benefit. Let me give you another benefit of Chapman Kolmogrov equation. Write this as a benefit, for example, in the terms of population. Just write it as it is. So imagine UN is the distribution of the random variables, the n random variables from x bar to x. Okay? That's kind of distribution factor. Let me write it this actually. So UN is what? So UN is the vector of row vector of probabilities. Vector of probability. And each of entry of this row vector is UIN. And the UIN is basically representing what is the probability that the random variable xn is going to be in the state I. Can you do this? What do you mean by that? So roughly, this is the distribution vector, probability mass vector of the random variable xn. So what would be the dimensions of this vector? Can you guess? How many entries are going to be in this vector? As many as the states you have. Because xn can be in the state, say 0 or 1 or 2 or 3. As many as the states you have. So if you are talking about finite, for example, states, then it makes more sense actually. Then you are then probability that is in that. Question: can I compute these probabilities? In other words, can I talk about that on nth day the weather is going to be exactly the state present? What do you think? What should be the way of doing it? So let me manage this. Then I'm like, right, the key interesting result is basically that if you want to know the state, this probability vector on nth step, so what you can do, and you know, for example, this probability vector on rth step actually, on rth step. Okay. Just simply multiply it with the conditional probability. That is what I'm saying. Imagine you know this new world, right? And you want to know new one. How can you do? Take the vector, take the current condition and just multiply it. If you want to know, for example, this probability vector after 2 steps. Take this part of the matrix and multiply it.
सर मल्टीप्लिकेशन
Sorry?
सर ये कौन सा वेक्टर है?
Multiplication would make sense. So this is a row vector of order, say 1 by order of S.
सही है.
Yeah? This is the matrix of order
S by S.
order of S. Wouldn't make sense another way. Here, augment is actually there. can show it very inductively, very easily. How can I show it? Like proof. So see, what actually you are doing, we are trying to fetch maximum information about the Markov chain and the states, states of the Markov chain by simply looking at the transition matrix. So we are kind of, trying to suck everything out of what you call transition matrix. What information you can fetch about the matrix, about the chain, it is very simple. So the probability that xn is j is going to be what? Obviously, if I am in state j, then you guess what should I write next? At the time n minus 1, I can be in what state?
Any state.
I can be any state. Right? So I can say that this is same as sum of the probabilities that currently I will be in the state j, given that on n minus 1 state I was in say state k, time probability xn
Minus 1. This here.
I was in this simple application of this probability that k is running in the state space S. Now what should be this done? This is simply Pij multiplied by the probability xn minus 1. Can you guess this expression? This expression is what? This expression is same as that. So if I write it in a vector form, so this is just one entry. So this is like and what entry of it? U and J.
PIK होगा.
Sorry?
JK.
Radio.
JK आएगा.
Radio करना.
Yeah, yeah. So yes. Obsessed with these eyes and this KJ. So if I write this in matrix form, just directly writing it, so we have the probability vector in the nth state is same as that you take the possession of x vector in the nth minus 1 state, or on the nth minus 1 is step actually and multiply it with the function of x. Okay. So that will be very easily argued that this is true. Okay. Let's keep playing with this very simple weather game, a weather example. And imagine this. In weather example, imagine this. Mu naught. So what will be the interpretation of mu naught? So it's a vector that contains the probabilities of weather being in the state wet and dry. Okay? Wet and dry. So I'm assuming it will be 5 by 4. And say 1 by 5 and 4 by 5. Okay, so what would be the interpretation of this? So it's a probability that today or whatever this not means. The probability that today would be wet. And that's a probability that today would be dry. Okay. will make sense in the sense of today, but you can think of what would be the weather today in the latter R cycle. It would be wet, very low probability, friction classification, and very high probability. And then I can ask what would be, for example, nu1? What is going to be nu1? So I introduce nu naught multiplied by the, I'm not interested in calculation, I'm just writing it. So 41 by 60 and 19 by 60. So transition matrix is allowing you to make prediction that what is, again I'm asking you, for example, to interpret mu1. So what would be the interpretation of mu1? What is the probability that tomorrow the weather we know is either going to be wet or dry? So this is the probability that it could be wet, and this is the probability that it will be dry. So provided that your transition matrix is true, or it's based on, or it's very sensibly made up. So usually when you are solving, for example, very practical problems, you become very sensitive about your transition matrix here, because everything comes out of it. Okay, and it's based on the experimental data. How you do the probabilities. So you fetch lots of data and you try to make out this transition matrix. The rest of things are depending on the transition matrix. Let's move on to another example. Simple example. Let's think about some of these things through that example. Imagine you have a sequence of independent variables. So I have a sequence of independent variables. That's what the only thing that I go over here. Nothing else. Question: does it form some Markov chain? Answer is let's think about it. Why? So I have Xn, I need to compute two probabilities by definition. So one would be, I think that Xn take Xn minus 1, and given that which takes Xn minus 1, Xn minus 1, X naught equal X. So what would be this probability?
Probably the same thing. Probably the same thing.
It should be same. Should be same as probability loss. Xn being X7. Okay. Next, this doesn't add anything in the. And obviously this would be same as if you have
Given Xn minus
Xn minus 1. That's minus 1. So it's a Markov chain. By the way, when this Markov chain is going to be homogeneous, do you remember the definition of homogeneity of a Markov chain? Let's form the conclusion. Very strong on this. Homogeneity means roughly that if you have Bij, the same as probability that n will be in the jth step, if you are in Jn, is n jth step, and on nth step you are in I. This is independent of
N.
mn. In other words, if you compute this probability from 0 to n, or 1 to n plus 1, or 2 to n plus 2 should be same, shouldn't change it. Therefore, you call it mod. So it depends on the number of steps. You know, it's steps, establishing steps. That's it. It doesn't depend from where you start or something. Those numbers. There would be a very interesting property that we talk about Brownian motion. Question. I want to tell, is this going to be a homogeneous stream? Is this going to be a homogeneous? How can I turn it into a homogeneous stream? What's going to do?
If the distribution is same. If the distribution is same.
If they are distributed. So, in other words, if you assume,
IIDs.
yes, you just add another assumption into yours, that along with being independent, if they are identically distributed, then it shouldn't be a problem. In other words, if you want that equality to hold, in other words, if you want this to hold, that okay, the probability of xn given j is same xn minus 1 I is same as x1 I. So that's just one step. Probabilities, and you want them equal no matter what one step you take, from 0 to 1 or n minus 1 to n. If you want them to be equal, then what will be the consequence? This will be same as you have the probability of xn equal to j, same as probability of x1 equal to j. In other words, for each step you have a fixed probability actually. What does it mean? Identically distributed. So x1 has the same probability as xn. So it must be identically distributed. So if you assume, so if I want them to be equal, and if I assume these two things, I can have this problem. That's a very abstract example. So every IID is a Markov chain, not only a Markov chain, but a homogeneous Markov chain. What would be the transition matrix in this case? What would be the transition matrix in this case? How does it look like that? Alright, so what we did so far, roughly, very roughly, not in a much rigorous way. We said you have a chain, defined chain, and chain corresponds to a transition matrix. You can fetch a lot of information about chain from the transition matrix, especially, you can talk about the future state of, the process. You can fetch lots of information about it from the transition. Okay? And what was the key thing that allowed us to do all those things? This Chapman Kolmogrov equation. That allowed us to do very interesting things. The next thing is, here we have to back into it, is to basically if you give me so the next thing is we are interested in, for a given chain, we are interested in knowing its long-term behavior actually. Okay, how it would stabilize actually. Would it stabilize or not? Okay, would it stabilize or not? How does it going to behave in long run? In other words, for example, if you talk about this pizza example, that you have 5 pizzas, 5 pizza places actually, okay, and you have people who are basically trying different pizzas. Okay, so I went to Pizza Hut and it turns out it's a new experience actually. And I went there, I didn't like it, so I went to Pizza House actually. So I liked it, I'll again go there. Then I thought actually, after some times the quality went down, so I'll switch to new pizza, or maybe I'll return back to, what do you call, Pizza Hut. So you can see that I can make a chain out of it. The question is, assume these 5, what do you call, shops are here in long run, very long run. The question is, our people are going to almost leave this switching actually. Are they going to always switch? Or in long run, as you get mature, you will stick with, one particular, pizza type shop. Because once you have tried a lot and a lot and a lot and a lot, then then you have these marketing people creating these strategies. And if they know that if you're gonna leave it like that, everyone is making the pizza the way they are making, they're not adding new thing into it. So people are going to stick to their, what you call favorite shops or favorite pizza places. How can we change it? So what do you need to do? So we need to break this chain. Give the offers and deals and do new things, and people will go again and come again and you can see that basically that all these things can give you, and that's what is happening. Literally, that's what is happening. These gigantic corporate industries, they have very specialized people who just look at everything actually when you enter into the shop actually. They can trace, the way your eyeball is moving around all the things. So they have lots and lots and lots of data. The data is power. So once you have data, and once you know that how people are behaving, you can either reshape them or reshape yourself so that you can guess them. Data is becoming power. They have a lot of statistical tools are depending on such kind of study. So the next thing is, as I said, if you want to study a chain in long run, because that's what our end objective is for the next discussion, then you have to look inside the chain. You have to look carefully, analyze the states, that how these states are related to each other. Now what we want to do, we want to classify these states. Let's do the classification of these states. Okay? The thing is, for classification, and explain the role. Classification of states. Even you can classify the states based on based on probabilities. So this is probabilities. So here's a definition. Here's definition. I would say the state I leads to J. In other words, you are in the chain. So let me make a chain actually, which I'll use for example as my primary example. Okay. So I'll use this as my primary example in many situations. So 1, 2, 3, 4, and 5, and 6. Okay. 1, 3, 4, 3, 4, 6, 4, 5, 6, 7. 5, 6, and 6. So imagine we have this chain. So I'm not writing probabilities. So when I'm saying I leads to J, it simply means I can start from the state I, and after making some number of movements, I can reach to the state J actually. So I leads to J. What does it mean? It means this. If I can find the number of steps and positive such that you have a positive probability from going to the state I to the J in n step. Okay. So I leads to J means that you have chances that in some number of steps you can eventually get from I to J. So in this chain, what do you think? Which of the states are going to lead to which? So can I say 1 leads to 2? Yeah. 1 leads to 3. 1 leads to 5? 1 leads to 5?
No.
No matter how hard you try. 6 leads to 4, 5 leads to 4, or 5 leads to 1, 5 leads to 1?
No, sir.
Or not. So you can go from 5 to 6, and 6 to 4. No, can't get. Can't get. Right? Are you getting the point?
Yes.
You see? So if I put different arrows, you can see that you have a very different chain appearing at within the same state. So I can treat this as that I have basically 2 small chains connected with this arrow. Right? This has a chain, this has a chain. Not a chain, but I'll call it a class. You can see what I mean at.
Yes.
That there are chances that in n steps you can get from state I to state. That's what I use to. Okay. I'm going to say I and J are intercommunicating. Okay, so I should write a symbol for it. So whenever I have to say I leads to J, I'll use this symbol. I leads to J. Okay. So this symbol means this. That you have positive probability and in some number of steps you can come from reach J. I would say I and J are intercommunicating. What do you think? What should be the definition of it?
I leads to J, J leads to I.
Yes. Intercommunicating. So if what happens? We can move from a state I to J and J to I. I is going to J to I. Yes. So we have a positive probability from some number of steps. Not necessarily the same and so it's not necessarily we go from I to J in 1 step, but we go from J to I in 1 step. As I said, we are planning go to 1 to 3 divided into 4 and 2 steps. One of them is statements.
One and two are interchangeable.
One and
Two are interchangeable.
intercommunicating. 5 and 6 are
Intercommunicating. Yes, yes.
but not 3 and 4. They are not intercommunicating. And if I have this, I'll use this symbol actually. I can only use intercommunicating. Okay. And I would say